All right, this is going to be the last video for Project 2 demonstration, R2DSP, and this last section is going to be over GSK implementation in C using the circular buffer FIR filter in C, which is section 3.4.3. So before we address the problem when coding in C of writing out all those coefficients by writing those coefficients into a separate C file and then reading that C file instead of having to type out all those coefficients. Now, the other problem that we talked about was the problem that the shift register is not very efficient at moving data around. So when you use the shift register, you have to shift every single element over by one, which can take up a lot of operations. It'd be much more efficient to use those operations to allow for more taps or for other things. So with that in mind, a more efficient way, instead of shifting each register, would be to use the circular buffer. So we'll close out of the previous project and open the new project. So this is the circular buffer. So the circular buffer uses dynamic addressing, which requires the use of pointers. Now, pointers are an advanced concept in C++ that is not normally covered in introductory to C classes. I have only taken introduction to C++, so I have not been formally introduced to pointers, but I can grasp a general idea of how pointers work. But because I'm not terribly familiar with pointers, I don't like to use pointers more than necessary. So this is going to be our example. This is an example from the book, which uses the same 31 tap filter. So if I open up the coefficient header, coefficient, it's the same example from the book, the 5 kilohertz at 48, or 5 kilohertz low pass filter at 48 kilohertz with 31 taps. So with that in mind, the thing about pointers is that pointers can represent the address of where the variable or data is stored in, or the actual value itself. This asterisk is called I think it's called a delimiter or something similar. But when the asterisk is in front of the pointer, that means you're taking the value at the address. When you see the pointer without the asterisk, it's referring to the address of the pointer, not the value that it's pointing to, the actual address itself. So when you initialize a pointer, you define what it's pointing to, the value it's pointing to's type. So this pointer, since it's delimited, means the value that it's pointing to is going to be a float type. And here we also have that buffer. And so we go over here and we have another pointer P. So this is going to take in the data, and I'm going to store the value at the input into the value, since there's the delimiter, into the value at the pointer. And then I take the output equals to 0 to set it up to initialize the output to 0. So now this is going to take the address at P left. So notice there's no delimiter delimiter. So it's going to take the address of P left and store it into pointer P's address. So that's the address. And then you're going to increment the address. So this is how we're going to circle around. We're going to increment the address, which will take the next memory location, all the way until this ampersand sign, when used in front of a variable, is used to define the address of that variable. So ampersand x left of n will take the memory address of x left n, which is the last element of the array. So it'll take the memory address. So it'll keep incrementing until you get to the last memory address. Then it will wrap around where it'll take the address x left. I'll take the address of x left and dump it back into P left. Now, when we're doing the dot product, this part's still going to be the same, kind of. So you're still going to take the output, but we're going to take the pointer P, we're going to take its value, and then we're going to multiply it with the coefficient, with the coefficients, and then you're going to sum it just like the regular dot product. And this shift register is now going to go into effect. So this shift register, or not shift register, circular register. So the circular register is going to then wrap around if necessary. So with all that, after it's wrapped around and after it's performed its dot product, it'll still output it just like normal. So the explanation is a little bit I'm not exactly proud of my explanation of that, but I'm not terribly familiar with pointers, but I have the general idea of what the pointers are doing. So into the coefficients, again, this example uses a 5 kilohertz low pass filter, sampling frequency 48 kilohertz. So I open up the DSP configure header. I make sure my sampling frequency is 48 kilohertz. So I can just run this. Now you won't see the advantages of the circular buffer right away in this example because the circular buffer allows for more taps, but the number of taps used here is not very large. It's still only 31 taps. And the shift register could handle the 31 taps. So the circular buffer can definitely also handle 31 taps without any issues. So this won't actually show much, but this is just to show the implementation of the circular buffer for now. And it might take, oh, it's configuring. So we'll give it a bit to configure. I'm recording. Okay. Okay. Well, if that's running, I guess I can talk about it. Oh, no, it's going. All right. Here we go. So it's low pass. I'm not going to send in signals higher than 5 kilohertz because that's going to be really high pitched and very annoying and headache inducing. But here's 1 kilohertz. Passes through no problem. I'll go up to 3 because 3 is a good limit for me. Yeah, that's yeah, okay, they all pass through. So this doesn't really demonstrate the power of the circular buffer because the number of taps here is relatively small. It's only, like I said, in this example is only 30 taps. And if the shift register can do it, then the circular buffer can definitely do it. So with that in mind, it's time to push the limits of the circular buffer. So using the same coefficient generator, I've also done the same experiment that I did with the shift register, but with the circular buffer to see the maximum number of taps I can use before the system, before the DSP processor can't process the data in time. So I did it for all the possible sampling frequencies, and here are the numbers I got. So if I scroll down, we can compare the circle buffer 8000 to the shift 8000. Notice how the number of taps right here looks like there's about 40 more taps here, and it looks like there's about 20 more taps here, and maybe 20 more taps here, 10 more taps, 5 more taps, 5 more taps, 5 more taps. So you can get anywhere between maybe at the lowest frequency you can get about 20 more taps. Not the highest frequency, you can get a higher frequency, you can get around 5 extra taps, which I don't know if that's a whole lot, but it is more efficient that way. Or you could use the same number of taps and use those extra operations to perform other things in your code instead of just only performing that dot product. So the rest of the code is the same. I have the sampling frequency set to 8,000 because we'll start with here. So we'll get 767 taps. So that's the number of taps coming in here. I'm going to shape my frequency response with an FIR filter, low pass, 1500 hertz, same as normal. I'm going to do IFFT shift, all that stuff. So, and then, yeah, we're going to extract all those. And then here, I changed the file path. Instead of the line above it, which was the shift register, I'm going to put it in the circular buffer project. So other than that, it's the exact same. So we'll just run this. So here's what our filter looks like. It goes down. So yeah, at 1500 it goes to 0. So if I close out of this project, and go to the circular buffer project. This code for the circular buffer is exactly the same circular buffer, and the same references to the same file, but the contents of this file have been changed based on that MATLAB script that I just wrote. So notice how those 767 tabs. So here we go. Scroll all the way down here. 767 tabs. All right. I need to configure the DSP header to change the sampling frequency from 48,000 to 8,000. All right. So now we can just run this. All right. Building. All right. So filter is running. If I take a 1,000 hertz sine wave, pass it through, no problems. Take the 2 kilohertz sine wave, pass it through, you get nothing because the low pass filter has filtered out everything above 1500 hertz. So that's the circular buffer. And notice how the number of taps was 767. 767 taps, which is larger than the maximum number for the shift register, is only 723. But still, even if it's more efficient, there's still a limit. So if I go over the limit, so I add one more tap. So now the filter has one more tap. If I look in here, it's now 768. Run this again. All right. Notice how there's like a popping noise. So if I take my sine wave, it'll pass through, but it's starting to pop, which means it's starting to not be able to do all the operations in time. And again, if I put the 2 kilohertz wave, you get nothing, but you still hear the pops. So that's for the sample frequency of 8 kilohertz. So we're going to do the same thing again for a higher frequency. So we're going to go to that 4800. So if we compare the 48,000, 114 to 120, so you get about 5 extra taps, about 6 in this case, but you get about 5 extra taps at higher frequencies. I run this script, I get my coefficients. Notice how since I have less taps, the filter does not look as nice, it looks more wavy, so we can expect to see some more problems in our frequency response. So if I look into my coefficient header, I have 120 taps now. I changed my settings from 8 kilohertz to 48 kilohertz. And I run this. So then I run this. And it's done. All right. Okay. Take the 1 kilohertz sine wave, pass it through. No problems. Take a higher frequency signal, just 3 kilohertz. Oh, pass through. Oh. So what I was talking about is passing through the 8 kilohertz signal, or 3 kilohertz signal, and it passes through because I messed up. So going back to the MATLAB code, I forgot to change my other settings. So the sampling frequency, I still have it set to 8,000. So if I quickly change this now to 48,000, which is 6 right here, keep the 48,000 taps, run this again. This should work better this time. So now we have the correct number of, we have the correct sampling frequencies, so everything should be better this time. 120 total taps. I run this again. And alrighty, here we go. 1 kilohertz sine wave passes through, no problems. 3 kilohertz sine wave, it's attenuated very much so you can't really hear it because of the low pass filtering has removed it. So, but I think if I turn the volume up to max, you might be able to hear it slightly. because it's been attenuated greatly, but you can still slightly hear if I turn the volume all the way up to max. So that's because our filter is not perfect with the limited number of taps we can get at higher frequencies. Make sure I'm recording still. Okay, so with that now in mind, if we take it one more tap further, so we do that. So now the number of taps has increased by 1. So now we're running 121 taps. Go back into Code Composer and look at the frequency, or not the coefficient header file, 121 taps. So then, am I at 48 kilohertz sampling frequency? So that if I run this, all right. And you notice you get digital static or garbage noise because the number of taps is too large. The buffer or the processor can't perform enough all the operations in time, so you get garbage at the output. And so that's the two main ways we're going to address those are the ways we're going to address the problems with the original brute force design. So just to recap real quickly, the brute force design had two main problems. The first problem was having to type out all those coefficients, and we solved that problem by creating a script to create header files with the coefficients inside them that we can read from. The second problem was that the shift register was not as efficient at shifting data and required a lot of operations. And we can fix that by using a circular buffer instead of a shift register, which is more efficient, will allow us to use more taps, and the increase in the number of taps will allow us to have more accurate filters. But still, even with efficiency, or with the circular buffer for efficiency, you notice that the number of taps that we can get at higher frequencies is still limited. See, it's still less than 100. And when I was performing those tests at higher frequencies, you could still hear the signals in the stop band because they weren't attenuated all the way to 0, but they were heavily attenuated. And that's the main drawback with FIR filters. The FIR filters still require a large number of taps to be effective. When designing an FIR filter, and you need a lot of taps for it to operate as desired. If you want to use fewer number of taps, you'll have to use an IIR filter. But IIR filter design will come in a bit later. Other than that, the shift register and the circular buffer are the two ways, with the circular buffer being more efficient, and we use our MATLAB code to generate those coefficients so we don't have to type them all out. And so this concludes all that is on Project 2. And a brief recap, we demonstrate all these audio effects. The audio effects we demonstrate in the first part, we're going to come back to all of them. And then in MATLAB, we implemented the design philosophy on how we're going to buffer the data and then perform the dot product. And then these 3 steps were implementing it in C. So the first step was just implementing it through brute force, which wasn't very efficient. And the next step, we developed the coefficient header files. And in this last step, we used the circular buffer. And we also noted that the maximum number of taps for circular and shift registers with circular buffers being more efficient, they can use more taps. So the FIR filters with the circular buffer are slightly better than the shift register because they can use more taps. And that will be it for Project 2's demonstration.